Unit 2 is about thermochemistry, so energy and the energy relationships during chemical processes. We're going to use this first set of videos, so I got to break this up into two parts. We're going to use these first two videos to kind of introduce the terminology of thermochemistry, energy change, so on and so forth, and then we'll get into measuring them and calculating the energy changes and so forth in subsequent videos. But like I said, we're going to split these two, this introductory stuff up into two video clips, so you've got two of them to watch. All right, so start off with what I think of as a really poignant quote. With the exception of energy from the sun, most of the energy used in our daily lives comes from chemical reactions. That's actually a sentence in your textbook, which I think is pretty cool. Kind of drives home the fact that, you know, our lives everywhere are dependent upon chemistry. We can't do anything without it. So, taking a look at energy, let's get some definitions down here. So energy can be defined as the capacity to do work or to transfer heat. So what's work? Work is the energy used to cause an object to move when a force is placed on it. So physics people, work equals force times distance. And then heat is the energy used to increase the temperature, to change the temperature of an object. Units for energy. Typically, we use joules, which can also be expressed as kilogram meter squared per second squared. So you can see the force times the distance in there. Kilogram meter per second squared is a force, and then meter is your distance. So there's your force and distance expression. But there are other units. A calorie is equal to 4.184 joules. Calories, obviously, we talk about when we are consuming food and talking about the energy that we get from food. However, the labels on food actually show food calories, which is not a typical calorie, it's actually a kilocalorie. So labels that you're reading, if something has 120 food calories, it actually is 120,000 normal little calories that we use in chemistry. Two most important types of energy that we work with. Kinetic energy is the energy of motion. You've got this equation, the energy equals 1/2 mass times the velocity. So that's speed. And then potential energy actually is a pretty important idea. It's the energy of position, or stored energy, more importantly, for chemists. So where do we find potential energy in chemistry? Well, it's stored within the chemical bonds. It also is part of the electrostatic attractions and repulsions that we see. All right, so let's focus a little bit on this potential energy. Kinetic energy is easy. We can measure kinetic energy through temperature changes, the speed of the molecules, how hot something is, how cold something is. But potential energy is a little bit trickier. So we're sort of talking about potential energy, which is really the result of particle interaction, using the concept of Coulomb's law. So you actually learned this in a sense during first year when we were talking about lattice energy, the attraction between cations and anions in an ionic crystal. Excuse me. If you remember, the two ideas that made a crystal lattice strong was small size and large charge. Well, here are those two ideas expressed in a chemical equation, a mathematical equation. The potential energy of the electron attraction, the electrostatic charge, is equal to a constant times the charge of the two particles divided by the distance, and there's our constant. So you can have two kinds of charged particles. You can have like charges, or you can have unlike charges, opposite charges. So obviously with like charges, you get a repulsion. So if you were to bring two electrons close together, the energy associated with those electrons is a high repulsive energy. But as they move further apart, that repulsive energy is going to decrease. On the other hand, if you have opposite charges, you're going to have an attraction between them. And so the closer you get them together, the stronger the attraction is going to be, the stronger the energy of attraction is. And as the distance gets larger, now their energy starts to decrease. So the closer you keep them together, the more influence they have on each other. So the higher the energy, either repulsive energy or attractive energy. And that's going to change as the distance goes. All right, so we've got the system and the surroundings, two terms that you had seen first year. Remember that the system is the chemical that we're interested in, and then the surroundings is everything else. The flask itself, the lab bench, the air around it. But remember that we don't move out too far away from the chemical and consider the surroundings too far away from the chemical. Energy's not going to change that much. All right, so let's just do one quick review of the following processes I have examples of listed here. What's the system going to be? So water being heated in a tea kettle. What's the system? Yep, water. An ice cube melts in the sun. What's the system? The ice cube's the system. And if we have sodium fluoride dissolving in water, what do we consider the system? We consider the sodium fluoride the system, not the water. It's the chemical that is changing that we're most interested in. And then, of course, if we get to the surroundings, going back to those three examples, what's the surroundings with the water being heated into the tea kettle? Well, you've got the tea kettle, you got the stove, you got the flames from the stove. With the ice cube melting in the sun, what do you have? You've got the container, you've got the air, you've got the sun itself. Sodium fluoride dissolving in water. The water's the surroundings, the container, whatever you have it in, maybe a little bit of the air, but not much. All right, so different kinds of systems that you can explore. For us, we're most interested in a closed system, but let's take a look at all three. So an open system is one where you can have energy and matter exchanging with the surroundings. That makes it really difficult to keep track of what's going on. So in chemistry, we don't want a closed, or we don't want an open system. We want a closed system, because in a closed system, you have energy moving between the system and the surroundings, but the matter does not. The chemicals stay in the system, so that's a good thing. And then an isolated system, which is one, and for us in high school chemistry, hard to control, one in which neither matter nor energy is exchanged with the surroundings. We don't have equipment to be able to do that kind of thing. So for the most part, we're focusing on closed systems. So as far as that energy change goes, just remember that the first law of thermodynamics says even though you're having energy changing within a system, energy is not being created or destroyed. It's simply changing forms or moving from one object to another. It's leaving the system and going to the surroundings or something like that. Energy is always conserved. So if something's losing energy, that energy is going into the system as heat to heat up the system, or energy is being absorbed by the system in order to create lower energy bond or higher energy bonds or something like that. All right, we cannot measure the total energy, the kinetic and potential of a system, which is called the internal energy. The only thing we can do is measure how energy changes. And so energy can change in two ways. It can change from heat and it can change from work. So let's take a look at how that translates. So if a system is gaining heat, we call that a positive increase in Q. That's going to increase the total energy of the system if the system gains heat. If work is done on the system, now it's also increasing energy. So a plus for work being done on the system also means that the energy of the system is going to increase. However, if the system loses heat, obviously it's losing energy, and that's also always associated with a negative. Likewise, if the system has to do work, so for example, a battery is generating energy to run your phone, the battery being the system is doing work, it's losing energy. So its net loss is represented by the negative. So keep that in mind, because there's two ways that we can change the whole energy of the system. All right, so the internal energy of the system, although not measurable, has a fixed value for a given set of conditions like temperature or pressure and so forth. The internal energy of the system is considered an extensive property because it does change with the quantity of matter that you have. The more water I have at a certain temperature, the more total energy that quantity of water has. If each molecule has the same average kinetic energy, more molecules still means more total energy. So that's what we're talking about there. It's an extensive property. But it also is something called a state function. Internal energy of the system is considered a state function. Q and W aren't, but let's take a look at what state functions are. A state function is a property that is determined by the state of the system, regardless of how that condition was achieved. So the pathway that is taken is irrelevant. It's the starting point and the ending point that's important. So things that are state functions, energy, pressure, volume, we don't care how the temperature changed. If we added heat continuously, or we added bursts of heat and the temperature went up slowly and then it dropped a little and then it went up some more, we don't care how the energy change happened. We only care where it started and where it ends. So the change in energy is what's important in terms of initial and final states, not how we got there. So here's a nice visual. So you have two hikers. Their potential energy increases the same because they start at the same point and they end at the same point. But if you look at the pathways they took, one guy took a very circuitous route while the other person took a pretty direct route. Doesn't matter that he took more time to get there. He still wound up at the same position. So energy, change in energy, doesn't care about the pathway. It only cares about initial and final states. That's by definition a state function. You're going to see a few other state functions as we go through various units. All right. We know that there's exo and endothermic reactions, but for now, we're going to pause and pick this up at the second video.